as well as the first. So the first experiment that we're going to do is called the heat capacity of the calorimeter. And a calorimeter is this device that we're going to use to measure heat and temperature changes. So let's take a look at the calorimetry setup that we have here. So what we want to know is we want to know how temperature changes with heat. So if we put heat into the calorimeter, how much heat is required to raise the temperature of the calorimeter by degree C? So normally when we look at the relationship between energy and temperature, we think of heat capacity. And normally when we think of heat capacity, what comes to mind is specific heat. But here, we're not. The heat capacity of the calorimeter is, how many calorimeters do we have? Just one calorimeter. And so normally we're interested in how many joules of energy it takes to heat up a gram of substance by a degree C. But we only have one calorimeter, and so this is going to be joules per degree C, or one, we could put in here 1 calorimeter. And so how many joules per degree C? And so what I don't want to have to do is I don't want to have to weigh this or do anything else. You want to weigh how many grams? This is going to be styrofoam cup. Actually, this is our calorimeter here. Our calorimeter is going to consist of 2 styrofoam cups, just so we can get double insulation, and a plastic lid. That's the calorimeter, but there are other components. We need a temperature probe. We're not going to use a regular thermometer. We're going to use these. And this is just a stainless steel case. Inside we have a thermocouple. The thermocouple, there's 2 metals that are connected, and the resistance of that connection changes with temperature. But we have to protect the metals from oxidation, so that's why they're enclosed in stainless steel here. That stainless steel is very unreactive, so it serves. And so our calorimeter is like this. It also includes maybe a beaker to hold the calorimeter, like this. And so we want to know how much heat is required to raise the temperature of this whole thing by degree C. But we also have to worry about heat leaking out. Do you see the hole in the lid here? The hole's kind of big, so heat leaks out. And then if you look at the lid's all cracked. Heat leaks out there. And are styrofoam cups perfect insulators? No, so heat leaks out there. And so when we say the calorimeter consists of multiple components. The styrofoam cups, the temperature probe, the lid, the air trapped inside here, the beaker, the air trapped inside here, and then the air outside here. Not only that, the heat can dissipate out into the air in the lab, and then it could dissipate onto the countertop and everything else. So everything else we call the rest of the universe. And so this is going to include, so the calorimeter includes all that. Hopefully not too much heat leaks out into the rest of the universe, otherwise it's not very well insulated. And so here we're just going to measure temperature changes. So we're going to dump in some heat in here and measure the temperature change. But measuring the temperature change of this is going to be difficult. And so what we'll do is we'll put some water in thermal contact with this. If we put water in thermal contact with this and then we dump in heat, then we can measure how much heat is absorbed by the water, and in turn the water is in thermal contact with this, so it'll tell us how much heat is absorbed by the calorimeter. And so basically this is what we want to measure. We want to measure, if you put a hot cup of coffee in here and just let it sit, you know, is it going to stay hot forever, or will some heat leak out? Some heat will leak out. And that's what we call the heat capacity of the calorimeter. The heat capacity of the calorimeter is going to tell us how much heat leaks out and what the temperature is going to do as it drops. So the setup is going to be like this, but I'm going to change the setup from how it is in the lab manual. So what we're going to do here is, actually, we'll just look at it based on the graph. So, excuse me. So if we put hot water, let's say I'm going to put 50.0 grams of hot water into styrofoam cups. Is it going to stay hot? No, what's going to happen is it's going to start to cool down. And then let's say I have 50.0 grams of cold water. It depends on how cold the water is. And so the water that we have in the tap, this is coming out of underground pipes, and the underground pipes might be a little bit colder. So if the water coming out of the tap is a little bit colder than room temperature, then the water coming out of the tap will warm up. And so the hot water is going to cool down, and maybe the cold water will either stay stable if it's at room temperature, or warm up slightly if it's a little colder than room temperature. And then we're going to monitor the progress. We're going to monitor the progress because what we need to do is we need to transfer the heat at a point where we know what the temperature is, but the temperature is constantly changing. If the temperature is constantly changing and we want to transfer the heat from the hot object to the cold object, then we need to know the temperature at the point where we mix it. That is, mix the hot water and the cold water. And so we're going to monitor the temperature for 6 minutes, or 5 minutes actually. We're going to monitor the temperature for 5 minutes, and then at minute 6, we're going to mix everything. And that means all the heat is going to go from the hot to the cold. And so the cold is going to warm up, the hot's going to cool down. But when we have this mixture, the mixture is still above room temperature, and so the mixture is going to start cooling down as well. And so what we need to do here is we need to monitor the temperature as it cools down the mixture. And so the tricky thing is here, we need to know the temperature of the hot, the temperature of the mix, and the temperature of the cold all at the same time, all at 6 minutes. We aren't going to be able to do this. The only way we are going to be able to do this is by extrapolation. So, you know, when we have the hot water here, we have to open the lid to pour in the cold water. When we open the lid, the thermometer, the probe is going to be out of there. And so here we're going to forward extrapolate this out to time 6 minutes. Here, the cold water is either going to be flat or warming slightly. And then we're going to forward extrapolate this to 6 minutes. And then for the mixture, we're going to back extrapolate this to a time at 6 minutes here. So what we end up with is this. Actually, this looks linear, but it's more of a curve. And so, especially it's hot. When the hotter it is, the more rapidly it cools. And as we get closer to room temperature, it starts to slow down. And so normally what we'll do is we'll draw a smooth curve like this. So it depends on how hot your water is. This is kind of flat here. It doesn't look like much of a curve. It should be. But this looks linear. The cooling is non-linear. But when you get, closer and closer to the room temperature, it's so slow, the change, that it looks fairly linear. And then we forward extrapolate this and see what the temperature is at 6 minutes. So we need a vertical line here at 6 minutes. To figure out what these three temperatures are. So let's do it. So these three temperatures here do not come from the thermometer, or call it the thermocouple, or the temperature probe. These three temperatures come from the graph by extrapolation. And so this temperature will label T hot. This temperature will label T cold. So the first thing we're going to do is we're going to get some hot water. It's probably better to use DI water for this. So we get some hot water. We just need this like maybe hotter than 85 to 100 degrees C. And then we're going to measure 50 milliliters. 50 milliliters is 50 grams, basically. So we'll measure 50 milliliters of hot. But what's going to happen when we pour this from the beaker into the graduated cylinder, it's going to cool down. It's going to warm up the air. And then when we pour it into the grad cylinder, it's going to warm up the grad cylinder. And then we'll pour it into our beaker. By the time we pour it into the beaker, is it still going to be 85 to 90? No, the temperature is going to be way lower. So probably we want to be on the higher side. Maybe 90 to 100 might be better to start. We only have a 25 milliliter grad cylinder, so you have to do this twice. So hopefully by the time you get the hot water in here, it's still hot. Then we're going to put the cold water in here. The cold water, we don't have to worry too much. Temperature is not going to change much. There's lids on this. So, what do you think would be better? Would it be better to pour the hot water into the cold cup or the cold water into the hot cup? Hot water into the cold cup or the cold water into the hot cup? Which one would lead to less error? The pouring the cold water into the hot cup would lead to less error. Why? The reason is because when you are ready to pour this, we're monitoring the temperature like this. We're trying to extrapolate the temperature. What happens when you break the lid off the hot water? Is it going to cool faster or slower or the same rate? It's going to cool faster when you remove the lid. What happens when you pour the hot water in cold air? It's going to cool faster. So all of a sudden now we're no longer on this trend. It's going at a more rapid trend. Are you taking measurements then? No, when you're breaking the lid and pouring this, you don't have your thermocouple in there, and if you had your thermocouple in there, we need to know the rate of cooling, which we don't get. And so that screws up the experiment. But the experiment is written this way because logically you want the cold here and the hot here, but we're not going to do it that way. Instead, what we're going to do is we're going to leave the hot water nicely sealed, and then we can break the lid. If I break the lid off the cold water, do I have to worry about the temperature changing much? No, it's already at room temperature, right? And so I don't care if the lid's off here for a long time. It's not really going to change much. If I pour it through room temperature air, is that going to change the temperature much? No. So what I want to do is when I'm ready, this is what I'm going to do. Right before 6 minutes is up, so you have to keep track of the time, like 10 seconds before that. We're going to pop open the lid a little bit here, and then pour the cold water here, and then seal it quickly, and then just stir it up like this, or however you want to stir it up. Okay, so we're going to have this. That's going to define it, because either of these can act as our calorimeter. You know, the cold or the hot, doesn't matter because they're just two styrofoam cups and a lid. That's it. And so this is going to change this. I'm going to pour the cold into the hot. If I pour the cold into the hot, then I'm warming up not just, actually I'm not, I'm warming up only the cold water. So if I pour the cold into the hot, the cold water warms. But what cools down? What cools down is the hot water plus the hot calorimeter. So what's going to happen is the cold water warms. This I'm going to call my system. And then the hot water plus the hot calorimeter. The calorimeter consists of everything. The cups, the lids, everything. Cools. This I'm going to call my surroundings. So the system's going to absorb heat from the surroundings. Now we're going to apply the first law of thermodynamics, which is Q of the system is equal to minus Q of the surroundings. Whatever heat is lost by the system or gained by the system comes from the surroundings or goes to the surroundings. How much heat is gained depends on the mass of water. In this case, 50.0 grams, times the specific heat of water, which is 4.18. A lot of people have the specific heat memorized because it's the same as the conversion between calories and joules. 1 calorie is defined as the amount of heat required to raise a gram of water by degree C. And since 1 calorie is equivalent to 4.18 joules, it takes 4.18 joules of heat to heat 1 gram of water by degree C times delta T cold. So how much did the cold water warm up? Well, going back over here, this would be delta T cold. And so we end up going to what we call T mix. T mix will be the final temperature. Here. This is T mix, 35.7. So delta T cold is just equal to T final, T mix, minus T initial, T cold. And so we could easily calculate how much heat was gained by the cold water. Where did all that heat come from? The surroundings. The surroundings consist of two things. What do the surroundings consist of? The hot water plus the hot calorimeter. So the amount of heat lost by the hot water we can calculate using MC delta T. Depends on the mass of the hot water, which is going to be 50.0 grams, times C, the specific heat of water, is 4.18. It's for water, times delta T hot. And so the hot water is going to cool down. This is going to be delta T hot here. T final minus T initial. So this is going to be negative. We're going to have a drop in temperature. Delta T hot is equal to T mix minus T hot. Since T mix is a lower temperature than T hot, this is going to be negative. And so the change in temperature was negative versus T cold, that was a positive change in temperature. Got hot. Do we weigh the calorimeter? I could weigh the beaker, I weigh the cups, the lids, and everything else, but do we weigh it? No, we aren't going to determine its mass. In fact, we're just going to treat it as just one object. And so how many calorimeters do we have? We have one calorimeter times the heat capacity of the calorimeter times delta T of the hot calorimeter. Delta T of the calorimeter is the same as delta T hot. Since the hot water and the hot calorimeter start off at the same temperature and end up at the same temperature. So delta T hot water is equal to delta T of the calorimeter. And so we set these two equal and then just plug everything in and solve for the heat capacity of the calorimeter. If no heat is lost, that is, if you put a hot cup of coffee here and the temperature never changes, then the heat capacity of the calorimeter is zero. It takes zero energy. It absorbs zero energy. If the heat capacity of the calorimeter is large, then it absorbs lots of energy. So if you have styrofoam cups like this, do you want a large heat capacity or a small heat capacity? You want a small heat capacity. In fact, you want something close to zero, something that doesn't absorb any heat. And then your coffee or tea will stay hot for a very long time. And so typical heat capacities for the calorimeter are in like 10 joules per degree C, something like that, a little bit of heat. 20 joules per degree C. But if you get like 1,000 joules per degree, that's 1,000 joules is a lot of energy you're losing out of the cups. It's probably calculation error. Or what if you get a negative heat capacity? Let's say I got a negative heat capacity. What does that mean? A negative heat capacity means, let's say I got negative 10 joules per degree C. That means in order to increase the temperature, I have to remove heat. In other words, if I put cold coffee in here, the cold coffee would warm up. Right? That is room temperature coffee. Or even coffee at 50 degrees C, it'll get warmer and warmer. So a negative heat capacity means that there was an error. And so what we're going to do today is we're going to collect our data for this and determine the heat capacity of our calorimeter using the calculations here. Okay, we're also going to do a few other calorimetry experiments. And so let me talk about those next here. What we're looking at is a case where both the system and the surroundings were objects. The hot objects cooled down, the cold object warmed up. But in the next experiment, where we deal with reaction 1 here, we're looking at a process. Now the process could be chemical. So this is a chemical change. This is a chemical change here. However, number 2 is a physical change. All of these processes are exothermic. So all of these release energy. Some processes are endothermic. when we have a process, then we define the system. So in reaction 1, what is our system? Our system is the chemical reaction. Here, for reaction 1. So what we're going to do is we're going to do this chemical reaction, and our system is going to generate energy. Where does that energy go? Into the surroundings. So now we have to figure out what are the surroundings. The surroundings are everything left over after the reaction has finished. And so the reaction itself disappears. You know, once the reaction's done, we just have what's left over, the products and energy. And so where does this energy go? The energy is going to go into everything that's left over. And everything that's left over is whatever you have in the cup. And so let's take a look at reaction 1 here of the setup. So we're going to put in 50.0 milliliters of HCl. And do you know the concentration of the HCl? .05 molar. And then we want to monitor its temperature. This would be the temperature of the HCl. And then over here in the other coffee cup, we're going to have 50.0 milliliters of NaOH. And the molarity of the NaOH? 0.00 molar. So which one's the limiting reactant? The HCl or the NaOH? The NaOH is the limiting reactant because we have less of it. And so we call this the LR over here. And over here we have excess. So how much reaction are we going to have? We're only going to have, well, you know, if I take the volume times the molarity, I'm going to get 0.0500 moles of NaOH. React. So that limits how much energy is produced. Energy is an extensive property. And so the more sodium hydroxide we neutralize, the more energy we're going to get off. But in this case, we're only neutralizing 0.0500 moles worth of NaOH. So do I add the acid or do I add the base? Yeah, I'm going to add the acid to the sodium hydroxide. So this one I don't have to worry as much. You know, both of these are going to be at room temperature, roughly. And so we're just going to monitor the temperature of this. We want to monitor the temperature to make sure it's not changing, or if it's changing, we want to be able to determine the trend here. Then we want to monitor the temperature of the sodium hydroxide. Hopefully the temperature of the sodium hydroxide is the same. but it might be slightly different due to different calibrations on the. So right before 6 minutes, what are we going to do? At 6 minutes, we're going to pour the hydrochloric acid into the sodium hydroxide. So the time equals 6 minutes. We're going to mix. And then what we end up with is a reaction. But does the reaction continue forever, or will the reaction stop? This reaction is very fast. The reaction is going to stop. When the reaction stops, it's released all its energy into the surroundings. So what are the surroundings here? Well, let's see. When we take HCl plus sodium hydroxide, what do we make? Yeah, H2O and NaCl. So we're going to be left over with water and sodium chloride and a little bit of excess HCl. And so I'm going to call this the salt water. So what's left over is we have salt water left over after the reaction, plus everything else. Plus everything else is called the calorimeter. So the calorimeter is left over. And so where does the energy go from the reaction? It goes into the salt water and the calorimeter. Those are two objects. When you add energy to two objects, what happens? When we add the energy to these two objects, they're just going to heat up. So the temperature should increase. There's going to be a temperature at 6 minutes, but that's not reliable. So what we do is we wait for the heating curve. That is the cooling curve here. And we have to watch out for incomplete mixing. So let me go back to this curve up here. Have you ever tried to cool down a hot bath or warm up a cold bath? Does the water mix instantaneously, or does it take time for the water to mix? It takes time for the water to mix. And so right when we mix it, these temperatures are not reliable. Or they might be, but these tend to be unreliable.
What unit number is this? Section?
Experiment number
Yes.
2. It's unreliable due to incomplete mixing. So we have to give it time for the cold water and the hot water to mix completely. So 3 minutes or 4 minutes is usually enough. But it depends. Sometimes it's not enough. Unfortunately, I need a moment to see if I can get Word to come back. I didn't want to do that.
May I ask what you were writing to Dr. Yamamoto?
I don't remember, actually.
I'm so intrigued.
I think that's an old one. Um, all right, unfortunately that is, I have too many things open maybe. All right, well that's gone, I think. Okay, I guess I didn't stop the recording. I was going to pause. I tried to pause the recording, but there'll be a gap there. Anyway, going back to this, these initial points are unreliable because it's primarily due to incomplete mixing, and normally you see a lot more variation in these. So they could be down here and then warm up here or wherever. What's more reliable is after it's completely mixed, then we want to see the cooling trend. So these points here we'll use to back extrapolate. And so these points up here are unreliable. And so we want to use this data to back extrapolate. And so we just want to work backwards and see what the temperature should have been if there was a nice cooling curve from here. So we'll just draw a nice curve and then go back. It's not going to make a big difference here, but something like this. And so now we have the three temperatures. We are going to have T hot, T mix at 6 minutes, and T cold at 6 minutes. Well, in this case, oops. The HCl and the sodium hydroxide should mix and react pretty fast. And so what we're going to see for this graph is something like this, maybe. We'll have the HCl and the NaOH solutions. They should be roughly about the same temperature. And so we want the temperature, we're just going to average it. So this will be the cold temperature here. And then the temperature is going to jump up. It's quite exothermic. And there could be some incomplete mixing, but once we get this, it should be stable. So the same thing here. These first temperatures can be unreliable, so we're not going to bother with those. Instead, I'm going to look at the trend once it's completely mixed. And so once it's completely mixed, I see the trend here. And I'll just draw a smooth line through here, back to 6 minutes. And so this is the T mix. This would be the T initial. And so T mix is T final. And so what warmed up? The surroundings warmed up. And so this will be my delta T here. And so what was my surroundings? What was my system? In this case, Q of the system is equal to Q of the reaction. Okay, once that reaction's done, then all that heat is absorbed by the surroundings. So Q of the surroundings here is going to equal minus, well, what do I have left over? What I have left over is salt water plus the calorimeter. And so the amount of heat absorbed by the salt water depends on the mass of the salt water times the specific heat of the salt water times delta T. The amount of heat absorbed by the calorimeter is equal to the heat capacity of the calorimeter times delta T of the calorimeter. I only have one calorimeter, and so the quantity is just one. I don't have the mass of the salt water though. Instead, I have 100. I know it's 50 milliliters plus 50 milliliters gives me 100. And I know to the nearest decimal point, so it's 100.0 milliliters of salt water. The problem is I need to know the density of the salt water. And the density of the salt water we don't have. And so what we're going to do is we're going to make an assumption. We're going to assume that the salt water is so dilute it's close to pure water. And so the density of the salt water, we're just going to go ahead and assume it's 1.00 grams per milliliter. In other words, it's going to be close to the density of pure water. I don't have the specific heat of salt water. The specific heat of salt water is different than the specific heat of pure water. But what I'm going to do is I'm going to assume it's going to be very close to that of pure water. And so here I'm going to use 4.18 joules per gram degree C. And then the delta T I'm going to get off the graph. Okay, this is going to be plus C of the calorimeter. C of the calorimeter comes from the previous experiment. Times delta T. And so all the heat of reaction was given to the surroundings. I should just say all energy of reaction was given as heat to the surroundings. All right, so this is going to tell me how much heat the surroundings absorb from that chemical reaction. And then we're going to do one more calculation after this. We're going to calculate delta H of reaction. This is called the heat of reaction. The heat of reaction is just going to equal Q of reaction divided by the moles of reaction. And so the Q of the reaction we're going to get from this calculation above here, and the moles of reaction we get from the limiting reagent, which is 0.0500 moles of reaction. And then we're going to change the units over to kilojoules per mole. Energy is intensive. It depends on how much. But the delta H is intensive because it's a ratio. It's kilojoules per mole. So if I have 2 moles, it's twice as much energy. But the ratio stays the same. All right, any questions on this? This is a physical process here. It's called the dissolution process. And it's also exothermic. So this one's exothermic. We have energy. This one's exothermic. We're going to have energy here. And so once the dissolution, once the dissolving is complete, where does all the energy go? All the energy goes into what's left over. And so we're going to take a quick look at reaction 2 here next. Reaction 2 is a physical process. It's the dissolution process. And so what you're going to do is you're going to bring a watch glass over to the stockroom, and then they're going to weigh out x.xx grams of solid sodium hydroxide. And then we're going to dump this solid sodium hydroxide into some water and our calorimeter. And so this is going to be 50.0 milliliters of water. And then Q of the system here is the dissolution process. And so the sodium hydroxide solid dissolves in water to make sodium hydroxide aqueous plus energy. Now, a process doesn't live forever. So once all the sodium hydroxide has dissolved, then we would have released all the energy involved in the process. And all the energy in the process is going to be absorbed by the surroundings. So all this energy goes to the surroundings. And so let's look at Q of the surroundings. Q of the surroundings is everything left over after dissolving. The sodium hydroxide. So what's left over? We have the sodium hydroxide solution left over, plus the calorimeter. That's all that's left over. And so Q of dissolution is equal to minus Q of the surroundings, which is minus Q of the sodium hydroxide solution, plus Q of the calorimeter. So any heat lost by the dissolution process goes into warming up the sodium hydroxide solution and the calorimeter. We need to know the mass of sodium hydroxide solution. We need to know the specific heat of the sodium hydroxide solution. And we need to know delta T of the sodium hydroxide solution. And for the calorimeter, we need to know the heat capacity of the calorimeter and delta T of the calorimeter. But the calorimeter and the solution are in contact, so delta T of the solution is equal to delta T of the calorimeter.
This is in the textbook, right?
Yeah. So this is going to equal, we know the mass of the solution because I have X grams of sodium hydroxide and 50 grams of water. So it's going to be 50X grams of solution. And so we probably know that to 2 decimal places. So 5X.XX grams of solution. Do you know the specific heat of sodium hydroxide solution? I don't. But it's dilute. So if it's dilute, we're just going to assume it's the same as water, 4.18 joules per gram degree C. So we're going to assume it's about the same as the specific heat of pure water.
Does the book state it differently? Like use different formatting, notation?
Like,
For the formula.
yeah, sometimes. Times delta T of the solution. Plus C of the calorimeter, this is going to come from the previous experiment.
Is that second over gram Celsius? That compound unit? 4.18?
Joules, sorry.
Joules per gram per second. I was going to say that's a gnarly compound unit. So.
Yeah, joules per gram degree C.
Joules.
Then we're going to calculate delta H of dissolution. Delta H of dissolution is just equal to Q of dissolution divided by the moles of sodium hydroxide. So we'll just go do a gram to mole conversion. And that gives us something called the heat of dissolution.
Describes what specifically?
That tells you how much heat is generated for every mole
Oh,
of sodium hydroxide that dissolves.
oh,
Q is the amount of heat that's generated for x.xx grams of sodium hydroxide. We could also do that.
okay. Yeah, why do we have the 5 components there? Is that for the specific one, right? Because it says 5 x dot xx.
Yeah. We could do Q dissolution divided by x.xx grams of sodium hydroxide. And this gives us joules per gram. This one eventually will give us kilojoules per mole. Yeah, joules per gram is useful as well. The lab asks you to calculate both. All right, the last reaction, this is a chemical reaction. So 1 was a chemical reaction, 2 was a physical process, and 3 will be a chemical reaction. In this chemical reaction, we're going to just scrape the solid sodium hydroxide into acid rather than water. This is going to make salt and water. So once all the reaction has completed, then we've released all the energy from our process. Where does the energy from our process go? Into the surroundings. And so what would constitute the surroundings? The surroundings will be everything that's left over. And so everything that's left over will be, well, the stockroom is going to give you a sample of sodium hydroxide. They're going to give you y.yy grams. Sodium hydroxide is very difficult to weigh. And so this is why you're going to get it from the stockroom. You're going to get it from the stockroom on a watch glass like this. And then when you get it, you should cover the watch glass. Do you know why we want to cover the watch glass? Because sodium hydroxide is what we call hygroscopic. Hygroscopic materials absorb water from the air. They can absorb so much water from the air, it'll form a little puddle of sodium hydroxide aqueous there. And it's very difficult to weigh. It's very difficult to weigh because the mass just keeps increasing. It doesn't stop. You know, you get a larger and larger puddle of water.
It's not too wet.
So what they're going to do is they're going to take it out of a desiccator and weigh it immediately. There's going to be a...
Us that weight?
What's that?
They just give us this.
And they're going to give you the weight. Yeah.
Will that be the 4 sig figs?
3 sig figs. We can't be too precise with this because the weight is changing. Yeah. And so for reaction 3, Q of the system is equal to Q of the reaction. That reaction, once it's done, releases all its energy into the surroundings. What will be the surroundings here? The surroundings will be salt water and the calorimeter. So again, we have salt water, so we'll just handle it the same way. We know how many grams. It's going to be 50 y.yy grams. And then we're going to assume that the specific heat of the salt water is the same as the specific heat of pure water, 4.18 joules per gram degrees C. And then we'll measure delta T. And so the same thing's going to happen. We're going to monitor the temperature, and the temperature is going to shoot up. And then we're going to forward extrapolate one set and back extrapolate another set. Usually when I have my data points, I'll try to use an X or something. Or if I use a dot, I'll circle it. You want to make sure the data point's visible. And so we go back to 6 minutes and we make sure we have the temperature at 6 minutes. We're not going to use the thermocouple temperatures. We're going to use the temperatures off the graph here. And that's going to be our delta T here. The calorimeter, we only have one calorimeter, so it's just going to be 1 times C of the calorimeter times delta T. The calorimeter and the product solution, that is the salt water, are at the same temperature. All right, so that's basically what we're going to do. Today we're only going to do the heat capacity of the calorimeter. For reactions 1 through 3, we're going to do that next time. And so for today, I'm going to help you set it up. So you'll need to check out the equipment. We're going to work in groups of 1, 2, or 3. And so go to the stockroom. You're going to get your, what we call the LabQuest. It's a vernier system. Up to 3, groups of 1, 2, or 3. So the LabQuest has replaced the CBL system. Both were made by Vernier. So we're going to use the LabQuest system. LabQuest is even easier than the CBL, so I'll show you how to set it up after you check it out. So what you need to do right now is to get the hot plates hot and get your water boiling. Okay, then go check out the equipment from the stockroom. What level of heat? 10.